welcome to this lecture course on noise control in mechanical systems with me, Professor Sneha Singh. And we have begun our discussion on acoustic metamaterial, and we saw that we have a passive AMM and we have an active AMM. Okay. And passive means no external energy is supplied, just it works by the internal structure itself, and active means that it needs some external supply of energy in order to manipulate the wave. And among the passive we had the resonant and the non-resonant type. Okay. And today we will discuss about one type of non-resonating AMM, which is the space coiling metamaterial. So, we will discuss about it, the working principle, the mechanisms of noise control and the resonance frequency. So, over here although this metamaterial can work without resonance also, but most of the times the space coiling metamaterial uses the principle of both its internal geometry. So, without the resonance itself it can work, internal geometry or path modification. We are trying to modify the path of the wave, plus we are also creating some resonance, and both of them are working together to attenuate the sound waves in a space coiling metamaterial. So, what is it? It is an artificially designed material, okay, to manipulate the waves. And what does it do? It controls the path that the wave takes. Okay. So, let us see, the term space coiling means that whatever the space is available, you have coiled it up into some maze like channels. Okay. So, you are not having a straightaway path, but rather the space is now made zigzag or haphazard, twisted and turned paths. Okay. So, what is happening that these materials, they instead of letting the waves move in a straight line, they force the wave to take a very coiled up and twisted path within a material. Okay. So, this allows the material to interact more with the sound waves for over a longer distance within a compact structure. So, now think about it. Let us say this example, we have this figure here. So, the dimension of this material is only this much, okay, but within this small dimension the wave is interacting over a much longer path. Okay. It is interacting over a much longer path within this material itself. Okay. So, within a compact size we have twisted the pathway in such a way that even in this compact size we are elongating the path of the wave propagation. So, the interaction is increasing. Okay. The wave is interacting more. It looks like the wave is interacting 20 to 50 times more than it would if suppose you had uncoiled it and made it into a straight line. So, the design, as you see, it is often small, intricate and twisted or spiral shapes, space coil shapes. So, in any way if you can twist the space around so that the sound wave have to turn around and go into the twisted and the maze like channels or maze like paths, so that they travel a much longer distance within a short physical space. Okay. So, a much longer path the sound wave is taking within a limited physical space as seen here. Okay. Within this limited size, the wave is actually going through a longer pathway and interacting with a material in a much longer pathway. This shows a metamaterial designed by us. You can see our research paper on the space coiling metamaterial. So, what we had done here is that a typical design of a metamaterial I am showing you. It looks like a black box from the outside, okay, a rigid box or a rigid cuboidal structure with two slit openings for the sound waves to enter inside the material. And then what happens once it enters inside the material? This shows us the air domain. This is the air domain. So, when it moves inside, it goes through these alternating pathways. This shows the sectional view of the metamaterial. Sound wave is incident here, and the entry of the sound wave has been blocked from all the sides. Okay. So, the entry of the sound waves is blocked from all the sides. It can only enter into the material and then get trapped inside the materials and dissipated. It does not have any other path to go out of the material. Okay. So, there is no transmission from the other end, and what happens within this small volume or within this small space, it is taking this much longer pathway. Okay. So, within this small space itself, it is taking a much longer pathway and is getting dissipated along the path. Okay. So, how this dissipation happens? Okay. So, how this dissipation happens is that, so first of all, one concept is clear, that we have a limited compact size material, and within that compact size material we are making the sound wave to go through a much elongated or a much longer path, and we are increasing the interaction between the material and the wave. So, whatever is this base material, this black material and the wave. So, we are increasing the interaction between them. So, we are there. So, when the sound wave is passing through, it is crossing the boundary of this solid material. So, the interaction has increased. Okay. So, because of this, the first phenomenon that happens is the wave compression. So, what it means is that, suppose, again I will come to this, suppose if this metamaterial was not present, but rather just a homogeneous material was present and the wave travelled from path A to B within this homogeneous material, what would happen? Suppose the wave has got a certain number of wavelength. So, suppose we have got wavelengths, okay, a certain number of wavelengths passing like this and reaching from point A to B. But now that we have elongated the path, okay, suppose we were able to cover some n wavelengths within this physical space. Now we have like this, I mean many wavelengths within the same physical space now, because the path length is so long that a lot of wavelengths are getting covered within the path, a lot of wave cycles we can observe. Before coming here. Okay. So, basically we are sort of compressing a lot of wavelengths within a small size. So, here suppose n wavelengths were there, here we are covering, we are capturing capital N wavelengths, where capital N is a much larger number than small n. So, basically within the limited size, more number of wavelengths are getting accommodated. This phenomenon is also called as the wave compression, because a lot of waves of the sound we are covering within the same physical dimension, and this leads to things such as phase delay, resonance control and so on, which we will see subsequently. So, it is sort of, it feels like the waves are now being compressed within a small volume. Okay. So, the first thing that happens because of this is that there is an effective refractive index control. We are able to control the refractive index of the material. Now, what is the refractive index of a material? It is simply defined as, just like in optics we have the refractive index as the speed of the light in air divided by the speed of the light in the medium. That is a relative refractive index. In the same way, the refractive index for acoustic waves, just like how it is for electromagnetics, can be defined as some value eta, which is the speed of sound in air. Okay, for the electromagnetics we consider the speed of sound in vacuum, but here for acoustic waves they cannot travel in vacuum. So, we take air as our reference medium divided by the speed of sound in the material under consideration. So, for the AMM this will become, for AMM space coiling metamaterial, eta will be speed of sound in air by speed of sound in the AMM. Okay. So, now if you once again look at the same schematic, and as explained in the previous lecture, if suppose only air was present, okay. So, the speed of sound in air in absence of AMM would be the distance, so would be the path length AB, because when there is no obstruction the sound will directly travel from A to B divided by the time taken. And the time taken is what? Here the time taken would be, or the length of AB by T, where T is simply the C naught 343. So, the length of AB by 343 or whatever is a C naught value, okay, that constant C naught value. However, when AMM is present, when the space coiling metamaterial is present, then to cover the same distance between A to B, the same displacement from A to B, it takes a much longer path. So, the time taken T would be what? It would be the length of this elongated path. Let us call this an effective length, which is the total length travelled by the sound wave within this metamaterial, which is this the length of this red line, which is the length of this red line. This is the L effective, okay, the net length divided by C naught. Now, this T dash here would be much larger. Why? Because this length has increased. So, it would be much greater than T. So, therefore, the speed of sound in AMM is what? It is the net displacement it is doing, that LAB by T dash. Now, it is covering the same distance at a much longer time. So, this speed is coming out to be much lower than the speed in air. So, the refractive index is what? Speed in air by speed in AMM, and this speed has decreased. Why? Because it is taking a much longer path to cover the same distance. So, this refractive index increases in value. Okay. So, we get a very high refractive index material because to cover the same distance we are making the sound wave travel a much longer path and it takes a much longer time to cover. So, basically we are slowing down the wave. What does a high refractive index material do? It slows down the speed, and that is the same thing which this metamaterial is doing. It is slowing down the speed of the sound, and once the refractive index has slowed down, okay, so this eta which has become much greater than 1, because the speed in air in absence of AMM is much greater compared to the speed in presence of AMM, because now due to path elongation waves have slowed down. So, when we have a high refractive index material, it affects how much the sound waves bend. Suppose the sound waves are travelling in the air and they encounter a medium with a higher refractive index, then they would bend, okay, and the higher the refractive index, the more bending you can achieve. So, when eta becomes much larger, then we have the bending of the waves or the refraction of the waves, the degree of refraction you can say also rises up. So, compared to a conventional material, we can be able to achieve a much larger amount of bending and refraction in the waves than in a conventional material, and this how we can manipulate it. Okay, what are the other principles? You have the enhanced wave interaction. So, the coiled up pathways allow for multiple reflections happening, multiple interferences, which gives rise to advanced control, okay, such as selective filtering, absorption. So, more interactions are happening, so more internal refractions and more interferences happen. Wave manipulation, definitely the wave travels gets lengthened without increasing the overall size. So, this changes the wave speed as already discussed. The wave speed or the assumed wave speed becomes much low. because now we have slowed down the waves, and this also leads to a phase delay. Okay, the delay in the phase happens, and then you can redirect the waves, negative refraction can also be achieved. So, these are the various phenomena that can happen in a space coiling metamaterial. But what are the mechanisms in this phenomenon? What is the chief mechanism of controlling the noise, or the chief mechanism by which the sound level is going to go down? So, the first is that the wave structure interaction has increased, because now the wave is travelling a much longer pathway and it is interacting much more with the material in a smaller size. Okay. So, because of that, the dissipation of the acoustic energy also rises up due to increased internal air friction, the increased scattering that happens. So, already I had explained that when the wave is travelling, it is taking a much longer path. So, there is internal friction in the pathway, and the longer the path, the more friction the waves have to face and the more decay will happen. Obviously, a sound wave that has to travel a shorter distance or a shorter path will have a higher magnitude than the sound waves that have to travel a much longer pathway because of the air resistance and the various other friction, the air friction and various other friction that take place in the path. Okay? And the friction is a quantity directly dependent on the length of the path. So, it increases and keeps attenuating the wave. More scattering happens at all the turns and the twists, and more dissipation happens. So, basically the dissipation rises up due to this. Then there is another phenomenon called as acoustic impedance matching. What happens is that here, when at certain specific frequencies, okay, the way these metamaterial are designed, that there is a specific phenomenon called as acoustic impedance matching. So, it happens so from our experiments, what we have observed is that this impedance matching happens at the resonance when the fundamental frequency of the internal structure is matching with the incident frequency. Okay. So, the frequency of the internal structure is matching with the resonance with the sort of incident frequency. Okay, that particular thing, what happens is that the surface impedance of the metamaterial. So, suppose you have the sound waves that are coming and hitting some material. So, the surface impedance matches with the impedance of the air. So, to the sound wave, it means that what happens when you have the same impedance? There is no reflection and all the transmission happens and the sound waves just go through. So, to the sound waves, it looks like there is almost no change in the acoustic medium and they just pass through. So, that phenomenon is called as impedance matching, and because when the impedance of the air and the metamaterial are matching, then all the sound waves, they are simply passing through. So, the absorption coefficient is going to approach unity. Why? Because no reflections will take place. It is essentially like I had explained, like for example, we have a closed room and we have an open window in the closed room. So, the sound waves can directly pass through the open window. The absorption coefficient is going to be 1 there. Why? Because it is like a medium continuity. There is no difference in the acoustic impedance. Reflections and change in the pathway only happens when there is a difference in the acoustic impedance. So, here in this case, what happens, the surface impedance of the AMM matches with the air, and at that point the absorption coefficient tends to unity. Now, if the other end of the structure is closed by rigid boundaries, so what happens, now we are allowing all the sound waves to enter into the material. Now, if we close all the other ends by rigid boundaries, so let me go back to this particular slide where we have this metamaterial. So, we are allowing the sound waves to enter into this structure, but we are closing it from all the sides. So, at resonance, almost all the sound waves would be able to enter the material. Why? Because now the impedance has matched. So, it behaves like a medium continuity and all the sound waves are entering and absorption coefficient is reaching unity. So, they get inside easily, but there is no means to go outside. So, they get trapped inside the material. So, they get trapped in the structure itself. So, what should be the condition for this acoustic impedance matching? So, simple, the impedance have to match, which means that the surface impedance of the AMM should be almost same as the impedance of the air, and we know that for normal incidence the surface impedance, the surface impedance is same as the small z, which is the characteristic impedance, okay, and this is rho c of the medium. So, this should be the condition for, so it should almost be same, okay. I can't say that it will be exactly same because theoretically it may be possible, but practically it never is achieved in reality that we get a perfect impedance match with exact equality. So, just the more it approaches this value, the better this phenomenon would be. So, which means that the relative impedance has to approach 1, okay, ZAMM by Z air has to approach 1, and we know that the relative impedance is an impedance term after all. So, it will have a real part and an imaginary part. So, an acoustic resistance and an acoustic reactance. So, this has to approach unity. If this has to approach unity, which means that the real part of the relative acoustic resistance should reach unity, and the imaginary part of the relative acoustic impedance or the relative acoustic resistance has to reach unity, and the relative reactance should become 0, so that we can achieve a perfect impedance. Okay? So, here just a simple derivation. Okay? So, this is again from one of our paper what we did. So, we had made that material that I have already shown the design for. This is the material that we had made, and then we observed its frequency response. So, what is the absorption coefficient over a range of frequencies, and what we observed that if suppose n is the number of channels. So, in this case let us go back. Here we have 1, 2, 3, 4, 5, 6. 6 channels are there. So, capital N becomes the number of channels. So, what we observed is that we modeled the same metamaterial, but we increased its number of channels and we observed its behavior. So, what we observed, as you increase the number of channels, the frequency shifts towards the lower value, okay, and then we also observed what is the real part of its relative impedance and what is the imaginary part of it. Now, at resonance where you are getting this absorption peak, there should be an impedance match. Okay, the impedance will match, which means all the sound waves are entering in the material. They are able to freely enter into the material at that frequency peak. Okay, at this peak frequency, they are able to freely enter the material due to the matching of the impedance. So, at these frequencies, this should be the condition, the resistance should become unity and the reactance should become 0. So, that is what we observed. When we observed the the resistance and the reactance at the peak frequencies, at all the peak frequencies, okay, what we observed is that the reactance was reaching as 0 and the real part, it did not reach exactly unity, but it came very close. Okay. And for this particular model, this was the closest to unity, and that is why this blue curve here, this shows the highest sound absorption. Why? Because there was the highest impedance matching here. And then the next nearest curve is this black curve. So, this had a much closer impedance match. So, this had a higher absorption coefficient at the peak. Then we had this black curve, this had a slightly lower peak. Then we have the green curve, which had a slight even lower peak, and then the furthest away was this yellow curve or the yellow metamaterial, whose peak was much lower compared to the rest. So, what we can say is that the closer the AMM is to impedance match, the SAC at peak would be closer to unity, closer to the maximum volume, which is unity. Okay. So, the higher the impedance match, the more would be the absorption coefficient observed. Okay. And how do you determine these frequencies at which this happens? Okay. So, now we know that this is the condition to increase the absorption, but at what frequencies? So, here the resonant behavior comes into effect. So, these space coiling metamaterials, they show resonance effects. So, that means that where the fundamental frequency of the coil matches with where the incoming wave frequency, it approaches the frequency of the coiled structure. That is the phenomenon of resonance. The incident frequency has the same frequency as the frequency of the structure. Okay. And in that case you have the maximum sound absorption, okay, and that is where the impedance matching also happens. Okay. So, the same way, so resonance happens. So, the sound wave is used up in driving the particles to high amplitude. So, let us find out the resonance frequency. Suppose we have got this space coiled structure and we are closing its end. Okay. So, we have some structure like this, sound wave is entering this pathway, whatever is your pathway, it could be any form, spiral, rectangular, like that, and then at the end it is being closed to stop the transmission. So, what does it behave like? It behaves like a pipe with one end open and one end closed. Okay? An open, closed, rigid pipe, and the fundamental frequency for this case is given by this value. Okay, so, for this particular AMM, it is the odd multiple of C. Okay? This is the speed of the sound. So, an odd multiple of C by 4 times of the L effective, where L effective is what? It is the total path length the wave takes within the material. Okay. So, the first fundamental frequency will come when n is equal to 1, which is C by 4 times the L effective. The second will come 3C by 4 times the L effective, 5 times this, and so on. Suppose both ends are open, something like this. It behaves like, okay, so both ends are open here and transmission is happening. So, it behaves as an open pipe, and the fundamental frequency for this is given by NC by 2L effective. So, which means that for this particular case it would be, the first would be at C by 2L effective, followed by 2C by 2L effective, followed by 3C by 2L effective, and so on. Okay. So, the knowledge of this frequency is important, because then you can predict that at what frequencies will you observe these peaks. Okay. These peaks should come at these frequencies, okay, these frequencies. Okay. So, this was some of the phenomenon. Then the other phenomenon is obviously the path wave elongation is happening and the manipulation is happening. We have already discussed about it, that how elongated path, it slows down the wave or delays them, and due to that the phase delay also happens, and the waves coming out from the other end of material, they will destructively sort of they have destructive interference with the other waves and they can cancel each other out. So, with this I would like to close the lecture on space coiling metamaterial, and thank you for listening.